Hi guys, welcome back to Calculus. This is Mr. Robeson. All right, so now that we know how to use logs and exponentials and how to simplify them with them, let's look and see if we can work on some derivatives with them. So derivative rules with logs. All right, so here is our derivative of an exponential. So this is the easiest derivative we will do all year. Derivative of e to the x is e to the x. It's the only function whose derivative is the same as the original function. It does not change. All right, kind of neat. All right, but most of the time we won't just have e to the x. We'll have e raised to something, and then we've got to do it like a chain rule. So we would rewrite it, and then we'd multiply by the derivative of the inside. All right, so if we have something there, we'd multiply by its derivative. All right, if it's not e, like if it's base some other number, like base 2, we'd just rewrite it. We'd do the derivative of the exponent, and we'd add in the natural log of the base. All right, so the natural log of whatever the base is. So if it was 2, we'd have a natural log of 2 in here. All right, we're technically doing that with e as well, but then natural log of e is just 1, so it just kind of disappears. So here are some examples. So the first one, all right, we've got y equals 5x times e to the 3x, and we want to find its derivative. All right, well, we've got x's down here on the bottom, and we have x's here in the exponent. We're going to do a product rule. So we still have first, 5x, times derivative of the second. We rewrite it, e to the 3x, times the derivative of the exponent. Derivative of 3x is 3. Plus the second, e to the 3x, times derivative of the first. Derivative of 5x is 5. All right. So now, oftentimes we'll want to set this equal to 0 and solve. So what we're going to do is we're going to try and factor out whatever we can. So they both have a 5, so we can factor out the 5. They both have e to the 3x, so we can factor out an e to the 3x. So we'd have 5e to the 3x. Our first guy, we just have an x and a 3, so 3x. Our second guy, we took out everybody, so it would just be plus 1. All right, so now if we're setting equal to 0, we would just set the 3x plus 1 equal to 0, because e to the 3x and times 5 are never going to equal 0. All right, so here's another one. Now we're dividing. Well, we just do a quotient rule. So our derivative, f prime, will equal low d high. Derivative of e to the x cubed is, well, e to the x cubed times derivative of x cubed. Not in the exponent, but down here on the regular plane with everybody else. It's just 3x squared minus high d low, square the bottom, and away we go. So 2 squared is 4, x squared is x squared. All right, again, we can factor out some stuff, like e to the x to the third is in both of them. We've got a 2 in both of them, so we can pull that out. The 2 is going to cancel out with the 4 down there, but let's just pull it out for now. So we got 2e to the x cubed. Here we're left with an x and a 3x squared. So that's going to give us 3x cubed minus, we pulled both of those out, so we're just going to put a 1 there, all over 4x squared. The 2 and the 4 cancel. Leave us with the 2 down there, and there's our answer. All right, we can also incorporate trig functions. And again, we have something with a variable here, t is our variable, and something else with a variable here, t is our variable. All right, we've got a base 2, so that means we're using this rule, the bottom rule here. We'll have an L and a 2 in there when we take its derivative. But again, we're going to do a product rule. So our derivative here, g prime of t, not x, is first, so 2 to the 3t, times derivative second. Derivative sign is cosine. Don't forget your trig stuff. Plus the second times derivative of the first. So remember, we rewrite it. So it's 2 to the 3t times the natural log of the base, so times natural log of 2, times derivative of the exponent, so times 3. All right, there's not much we can take out here. We can factor out the 2 to the 3t, but not much is going to come out, and it's really not going to simplify very much for us, but we'll take it out anyway. We're left with cosine of t plus, let's see, we got 3 ln of 2 as kind of like a coefficient, 3 ln of 2 times the sine of t. All right, and there is our derivative. All right, so here's one for you to try. Go ahead and pause the video, try and work it out, put it in your notes. I would treat this one as a product rule. So we got our first and our second. So our derivative, f prime of x, is first times derivative of the second. Derivative of e to anything is we rewrite it. No, that's squared, not cubed, squared. times derivative of the exponent. So derivative of x squared is 2x. Plus the second, e to the x squared, times the derivative of the first, 2. So we can factor out, or we can just look at our answer choices and see, okay, we want it to look like that. So let's see, we've got a 2x and a 2x, so that's 4x squared times e to the x squared. And here, this coefficient, this 2, would usually come out in front. So we'd have 2 e to the x squared. All right, looks like they switched the order on us, but yep, it's definitely x squared. So it looks like it's that guy right there. Yep, there it is. All right, log rules. All right, derivative of the natural log of just x is just 1 over x. All right, it's very basic, just 1 over x. Most of the time, though, we won't have just x in here. We'll have some sort of function in here. All right, and that whole function, well, it'll just go right down to the bottom. All right, but on the top, we kind of do a chain rule. It'd be like 1 over f of x, like we did 1 over x here. But then it's times derivative of the inside. So this always ends up being on top. So it's the derivative of the inside over the inside. So it's the derivative over the original. All right, that's how we take the derivative of logs. All right, if we have log with a base and it's not ln, really we're just using the change of base formula. Right? So for instance, this would change into the natural log of x over the ln of a. And then we take the derivative. This is a constant, so it's just going to stay down at the bottom. So the derivative of ln of x is 1 over x. So the x would come down, and we'd still have the ln of a down there. So it's not really a separate rule. It's just using the change of base formula first and then taking the derivative. If you want to memorize a separate rule, you are welcome to it. All right, so here we go. Y equals the natural log of 3x minus 7. So our derivative dy dx, or y prime, would be, on the bottom we have the same thing. On the top we have the derivative of 3x minus 7. Done. All right. Sometimes it's a lot easier if we do our log rules first to simplify. So if we simplify this first, if we have a lot of things here in the log, we would say this is the natural log of 3x squared plus the natural log of e to the 2x minus the natural log of 4. All right, we can't bring this exponent out because this 3 is stuck in here in front of it. But the ln here and the e can cancel out, and we just left with 2x there. Now if we take the derivatives, because we haven't taken the derivative yet, we were just simplifying first. So the first guy is going to be, let's see, we got 3x squared on the bottom times the derivative of that. So the derivative of that goes on top. We bring in the 2, it'd be 6x. That is going to simplify. Derivative of 2x is 2. Derivative of the ln of 4 is 0. All right? ln of 4 is just a constant. If there's no x's involved, it's just going to be a constant. Its derivative is 0. Gone. All right, we can simplify here. 6 over 3 is 2. X over x squared leaves us with 1x on the bottom. So we're left with 2 over x plus 2 as our answer. Some of you out there are probably saying, hey, we could have said this is the ln of 3 times, plus 2 times the ln of x, and then the ln of 3 would go away. Well, the 3 is going away here too. And the 2 here ends up on top, and we're left with 1 over x. 1 over x. Huh. So that works either way. All right, so here we go. Here's one with log. So usually what I do is I use my change of base formula first. I'd say this is the ln of x squared minus 4 over the ln of 2. And then when we take the derivative, on the bottom we'd still have that ln of 2. We'd also have whatever's inside here, x squared minus 4. On the top we'd have the derivative of that, 2x. But some of you out there are saying, hey, we could probably factor x squared minus 4 and we could break this up into 2 different logs. You could. You'd say this is x minus 2x plus 2 and log of x plus 2 plus log of x minus 2. But then we're still going to have to put it back together here. It's easier if we leave it like this in this case. All right, so we can still do all of our normal derivative type things like finding slopes of tangent lines, finding increasing and decreasing. We can still do second derivatives. We can still do implicit differentiation. All of that stuff still holds. So like here when it says find the slope of the tangent line, remember that means take the derivative and plug in. All right, so we're just going to take the derivative here, dy dx. Remember that is our function for slope. Is, well, inside goes on the bottom. And we get the derivative of that on top, 2x. Now we're just going to plug in 1. So this is when x equals 1 is 2 times 1 over 1 squared plus 1. So we get that our slope is 1. There it is. All right, can we find the equation of the tangent line? Well, we've got our slope. We need a point. So to find a point, we plug into the original. So we'd have y equals the natural log of 1 squared plus 1. So that's the natural log of 2. I'm not going to try and simplify that. We're just going to have the point 1 comma ln of 2. So it would be y minus this y value, ln of 2, equals our slope, m, which is 1, times x minus 1. There's our equation right there. All right, what about increasing, decreasing? Can we find when this function is increasing and decreasing? Y equals e to the x squared? Well, sure. We take its derivative. So that would be e to the x squared times the derivative of the exponent, which is going to be a 2x. All right, and now we want to know where is that equal to 0? Well, this will never equal 0, but this will definitely equal 0. That equals 0 and x equals 0. So we can do our number line chart here. We can say here's 0. We can have 2x as a factor and e to the x squared as a factor. E to anything is always positive. It's really easy. 2x changes at 0. So that means our y prime here would be negative, then positive. So our original function would be decreasing and then increasing. And this here would be a relative minimum. If we want the actual point, we plug it back in here. E to the 0 is 1. So there's our relative minimum. All right. And so we'll be decreasing from negative infinity to 0. And we'll be increasing from 0 to infinity. If you want to use brackets on the zeros, you can do that. That's perfectly fine. All right. We could also take a second derivative if we wanted to and find concavity. Second derivative is going to be a little more work here, but it works the same way. All right, so that's how we take derivatives with logs and exponentials. So that is it for 4.1. So check out the homework. It is a little bit long, so start early, please.